Okay, so now that we've talked about calculus, right, we are ready to talk about kinematics, and we see that actually kinematics is easy when you know calculus, because by definition, acceleration is by definition, the derivative velocity, and velocity is by definition the derivative of position, and position is a function of time. So yeah, so before we talk about the equations of motion, it is first worth defining a direction. So what I mean by that is that you may know that there are differences between scalar quantities and vector quantities. So example would be between the differences between the two would be scalar quantity with speed. It tells you how fast you're moving, but vector would be velocity. So velocity is a vector, whereas speed is a scalar. So velocity not only tells you the magnitude, how fast you're moving, but it also tells you the direction that you're moving in. And this, because of this distinction, right? Because velocity has a certain direction associated with it. When we define a direction, when we define x of t, right? Displacement. When we define displacement x of t, we need to define a certain direction in which it's increasing in. So what this means is that if I have a line over here that the particle in one dimension is moving in, then we define somewhere to be the origin, right, where corresponding to x equals to 0, then I need to choose which direction corresponds to increasing x. So if I choose the right side to be increasing x, meaning that if I move to the right, x increases, move to the right, x increases some more, and I move to the left, x decreases, move to the left, x decreases, then in this case, I would usually draw an arrow on this coordinate system, label this arrow with an x to indicate that moving right increases x. So, in other words, moving right increases x. And this is what we basically mean when we draw this arrow over here. This arrow is equivalent to saying that moving right increases the value of x. So if on the contrary, I drew a number line like that, I drew the world like that, right, and describe the world like this, then that will correspond to moving left increases x. And the reason why this distinction is important is because if I take the derivative of x with respect to time, remember the x of t describes the particle's position, right, or rather displacement. It describes the particle position as a function of time. If I take the derivative, this is by definition the velocity of the particle. So if I define, and remember velocity is a vector quantity, meaning that it has a direction associated with it. So if in the first case, if I define moving right to be corresponding to increasing x value, then an arrow to the right will be moving. We'll call this rightward positive, meaning that the vector is pointing to the right, and the particle's position is increasing as I move to the right. Right, the x value is increasing as I move to the right. On the other hand, if I had this other coordinate system on the bottom, right, then this would be called leftward positive. Because moving left, right, if the velocity is positive, then I'm actually moving to the left. Because velocity is positive means that my x value as a function of time is increasing. So velocity is positive, v of t is positive, means that x of t is increasing with respect to time. And if x of t is increasing with respect to time, right, in the first scenario, that means that the particle is moving to the right over time. Right? As time ticks, the particle is moving to the right. But in the second scenario, where we define x to be leftward positive, if the velocity is positive, that corresponds to a particle that is moving left. So that's why it's important to define a direction, right? This direction is something I can choose to impose. But the moment I choose it, I better denote where is positive, right? I better denote whether it's rightward positive or leftward positive. I can make the choice, but I must make clear to myself and anybody reading my working what the choice is. So I must draw these arrows labeled by the variable or the function in order to indicate to my markers, to my friends, right, which direction is positive for me or which direction is increasing for me. So yeah, so that's the importance of defining an increasing x direction, right? And after I pick this increasing x direction, I can write the function x of t, and I can take the derivative, and I can start doing 1D motion. What if I want to do 2D motion? If I want to do 2D motion, then I need to not only pick a direction for x, I also need to pick a perpendicular direction for y. So there's two, suppose, right, I pick x to be rightward positive. There's two possibilities now. One is that I pick upwards to be positive, and one is I pick downwards to be positive. Of course, you may be wondering, isn't this the more intuitive notion? When we graph y with respect to x, we always graph it like that, and that comes from math. But I'll give you an example where both scenarios, where both coordinate systems, right, both definitions for y, both definitions for increasing value of y kind of make sense. So in the first scenario, it would be projectile motion, right? Because y kind of very naturally corresponds to the height of the particle. Whereas for the second scenario, if we talk about a pendulum, right? If we talk about a pendulum and we're doing Cartesian coordinates, if we call the origin of where the string is attached to the origin, so this corresponds to x equals to 0, y equals to 0, then if I pick this, right, you can write y equals to L cosine theta, right? Whereas if you pick this coordinate system, then your y will need to be negative L cosine theta. So there may be scenarios where you might want to pick y to be downward positive instead of upward positive, and honestly, it's just a matter of convention. Usually in the 1D scenario, usually we pick right side to be positive by convention, because there's almost no reason for you to pick left side positive. So usually we stick to this convention over here. But again, it's totally up to you, right? Just stick to one and be clear which one you're choosing. And for 2D, you kind of have a choice depending on the scenario. But most of the time we still pick this. And lastly, for 3D motion, right? It turns out actually we do not have a choice anymore, because the moment you pick your x and y coordinates, right, the z coordinate, the definition of z increasing positive, the definition of increasing z direction is already defined for you. So if we pick y to be upward positive and x to be rightward positive, that automatically decides for you that z is out of the page, right? This means out of page positive, right? Whereas if you pick y to be downward positive and x to be rightward positive, that automatically defines for you z being into the page positive. And this notation over here, where we draw a circle with a dot in the middle, is, you can kind of think of it as an arrowhead, right? You know, your arrowhead has a tip at the end, right? And the arrow has a tail also. So this is kind of like the arrow pointing at you, right, out of the page. Whereas the scenario on the right over here is kind of like the arrow that's pointing away from you into the page. So when we want to draw vectors or directions in and out of the page, that's what we use. So yeah. So to summarize what we have said, right? In order to start describing kinematics, we already know calculus. So in order to start describing kinematics, we need to pick a definition for increasing x direction, increasing y direction, and that would lead to a definition for increasing z direction. And the reason why this leads to the definition for increasing z direction automatically is because there's a operation in the third dimension. The moment we introduce 3D, the third dimension, right? There's a product there's a product called a cross product between vectors, and in order for this cross product to 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 be able, in order for this cross product to match match our rules for this thing called right hand rule, where we use our right hand to define the cross product. In order for it to match the right hand rule, we need to pick the z direction to be x cross y. So we'll talk more about that when it comes to vectors, but we're ready now to talk about motion of a particle.